Alright, in this lecture, we're going to talk about image layers. So this is a fundamental concept of how Docker works, and it uses something called the Union File System to present a series of file system changes as an actual file system. So we're going to dive into the history and inspect commands and see how we can use them to understand what an image is actually made of. And we're going to learn a little bit about the copy on write concept of how a container runs as an additional layer on top of an image.
So what do I mean by image layers? It's actually transparent completely to you when you're using Docker, but when you start digging into certain commands like the history command, the inspect, and commit, you start to get a sense that an image isn't some big blob of data that comes and goes in one huge chunk, right? If you notice when we actually did Docker pulls, certain times you might see words that indicate that there's something that you already have, like you've cached some part of it already. And that's all comes down to the fact that images are designed using the Union File System concept of making layers about the changes. If we quickly just look at what we have in Docker, in our Docker images actually. So a while ago, we were playing around with the tags with Nginx, right? And we remember that the Nginx image ID is the same, and we had different tags for the same image name. So let's do a quick Docker history on Nginx, latest. What am I looking at here? This is not a list of things that have actually happened in the container, because this is about an image. This is actually a history of the image layers. And so every image starts from the very beginning with a blank layer known as scratch. And then every set of changes that happens after that on the file system in the image is another layer. And you might have one layer, you might have dozens of layers. And some layers may be no change in terms of the file size. And you'll notice on here that we actually have a change here that was simply a metadata change about which command we're actually going to run. And we'll cover that in a little bit when we go over the Docker file. But for now, you can actually see that this one added a huge amount of files that was 123 meg. And then we made a change here and a change here. And I happen to know because of Docker files that these are really just Docker file metadata information. And as you go up, we have some more data changes. And you'll see that this is actually quite different in another image. So if we go to Docker history MySQL, it has a completely different set of image layers. So let me draw this a little bit for you, and maybe this will help. So when we start an image, when we're creating a new image, we're starting with one layer. And every layer gets its own unique SHA that helps the system identify if that layer is indeed the same as another layer. Let's just say that at the beginning of one of yours, you might have Ubuntu at the very bottom. Okay, and that's the first layer in your image. And then you create a Docker file, which adds some more files. And that's another layer on top of that image. Maybe we use apt for that. And then in your Docker file, you make an environment variable change. Oops. And that together is your image. Okay? Now you might have a different image that starts from Debian Jessie. And then on that image, you may also use apt to install some stuff. Let's say MySQL. You might copy some files over. You might open a port. So each one of these changes that you usually make in the Docker file, but you can also make with the commit Docker command that we'll check out in a minute. So this is also another image. And those are all bundled together. But what happens if I have another image that's also using the same version of Jessie? Well, that image can have its own changes on top of the same layer that I have in my cache. And this is where the fundamental concept of the cache of image layers saves us a whole bunch of time and space. Because we don't need to download layers we already have, and remember, it uses a unique SHA for each layer, so it's guaranteed to be the exact layer it needs, so it knows how to match them between Docker Hub and our local cache. And as we make changes to our images, they create more layers. And if we decide that we want to have the same image be the base image for more layers, then it's only ever storing one copy of each layer. So in this system, really one of the biggest benefits is that we're never storing the same image data more than once on our file system. It also means that when we're uploading and downloading, we don't need to upload and download the same layers that we already have on the other side. Now, if you were to have your own image, and it was custom, that you made yourself, and then you added, let's say, an Apache server on top of that as another layer in your Docker file, and then you were to open up port 80, and then at the very end, you actually told it to copy in the source code, but you actually ended up having two different Docker files for two different websites. And every line in the Docker files were the same, except for that last little bit where you copied website A into the image and then website B. You would end up with two images. And we'll show that in a minute. This makes up one image and this makes up one image, but the only files that are actually stored is this one, this layer, and then this little layer, and then this little layer. So we're never storing the entire stack of image layers more than once if it's really the same layers. Now, how does this work with containers? So if you have your image, let's say we have our Apache image, and we decide to run a container off of it, all Docker does is it creates a new read-write layer for that container on top of that Apache image. And when we're perusing the file system in these things, all the containers and the images all just look like a regular file system. But underneath, the storage driver that's used by Docker is actually layering like a stack of pancakes, all these changes on top of each other. So if I ran two containers at the same time off of the same Apache image, container 1 and container 2 would only be showing, in terms of the file space, they would only be the differencing between what's happened on that live container running and what is happening in the base image, which is read-only. So when you're running containers and you're changing files that were coming through the image, let's say I started container 3 and I actually went in and changed a file that was in this image in the running container. This is known as copy on write. And what that does is the file system will take that file out of the image and copy it into this differencing up here and store a copy of that file in the container layer. And so now the container is really only just the running process and those files that are different than they were in the Apache image. So if we go back to our image list and we look at these commands again, and we look at the bottom one and see how the dates are different, we can actually see as this image got changed in Docker Hub and was updated over time that these changes haven't been changed at the very bottom of the layer in 4 weeks, and then the latest changes have been happening in the last 2 weeks. And oh, by the way, don't worry about the missing part. That's actually just a misnomer inside the Docker interface. It doesn't mean that something's wrong or it's misconfigured. What it means is that really this MySQL image right here is this image ID, and the other layers in the image aren't actually images themselves. Okay, they're just layers inside this image, and so they wouldn't necessarily get their own image ID there. Personally, I think it's a little misleading in the interface to say that, but that's how they wrote it. So now that we've got a sense of the history command to show us what an image might be made of, let's use the inspect command. So what this does is this gives us all the details about the image. And this is basically the metadata. Remember we talked about that an image is made up of two parts, the binaries and its dependencies, and then the metadata about that image. Well, inspect gives you back the metadata. And besides just the basic info like the image ID and its tags, you get all sorts of detail around how this image expects to be run. It actually has the option to expose these two ports inside the image so that you know when you want to start it, which ports you need to open up inside your Docker host if you want it to accept connections. You can actually see that environment variables were passed in, including the version of Nginx that it's running and the path. You can actually see the command it will run when you start up the image by default. And again, a lot of these things can actually be changed like we did earlier with the Docker container run command, but these are showing us all the defaults. And some other interesting information like the author, and down here at the bottom that it's an architecture of AMD 64, which is pretty much what all normal PCs and Macs run on nowadays. We don't really have too many 32-bit machines around, so this is just a standard 64-bit Intel architecture, and it's designed to run on the Linux OS.
Okay, a quick review. So we've learned a lot about images and how they're made up, and we find out that they're actually not that complex. Really, they're just a series of changes on the file system and metadata about those changes. And you learn that each layer has its own unique identity as a SHA, and they're only stored once on each system. So on each Docker daemon, each layer is only represented once in the file system. And that gives us a lot of savings in space as well as transfer time in sending images back and forth between registries like Docker Hub. And really, when you start a container, it's just a single layer of changes on top of an existing image. So it's actually usually very small. And we learned about the history and inspect commands and how they can teach us what's going on inside an image and how it was made.